All right, fancy time at the OK Corral. We're going to introduce the idea of a variable. Okay? So, why do we say variable versus what? A variable, so almost any word goes in conjunction with a different word because they're like opposites, like up, down, left, right, on, off, good, evil, that sort of thing. So, let's think about variables. So, what is the opposite of a variable? A variable, what does it mean? To vary, that's the root, right? To vary means to change. It can change. We don't know what it is. Right now in the pandemic we're all going through, maybe you've heard of it, there are people will say things, well, there are a lot of variables. There are a lot of variables. And it doesn't just mean there are a lot of variables in what's happening. It means actual, like, mathematical variables, because that's how a lot of these decisions are being made. So what's the opposite of a variable, in a sense, right? And that is what we've been talking about, which are constants. Okay? So in terms of like the coronavirus, we are considering our constants are like population size. We had to figure out the growth rate, and then that was a constant for a short time, but now it's changed, right? Right now, the main constant is population and ineffective federal leadership, but that's a different story. But constants in the world of math mean a number you absolutely know, okay? And when we go further along, we actually will use a variable for constants. Don't let it blow your mind yet. But a constant just means you know this number, okay? It is a knowable number and you know it. A variable is a number that can change, okay? And will change. And in fact, to get projections, for example, the growth rate on COVID and the idea of the flattening of the curve, as people say, we were looking at a constant growth rate that was going to stay unless we cut down one of the other constants, which was population. And by cutting down population, by playing hide and seek with the COVID-19, we actually then were able to reduce that constant, turned into a variable, and then swap it back. So it's like a little ping pong to hide from the virus. So in math, what do we do for constants? All my students can harken back. Everybody who's ever been to algebra. Use letters, right? And over here we use numbers. That's pretty simple. Letters, numbers. Okay? That just means that that's what we use. So for example, if I say, we're going to go back, and I say I want 3 5 times, okay? All 5 of you people out there are going to get 3 full cups of coffee. See, I had to say full because I only have a half left. I almost showed it and tipped it. Okay? So that means how many cups of coffee do I need? 3 5 times is 15. That is a knowable constant. Okay? But what if I say, I'm going to give 3 cups of coffee to any number of people who come into my world? Okay? Well, I don't know what that is, right? I don't know what that is. So I know a lot of my students and a lot of human beings ask all the time, well, when am I going to use this? Okay, well, we're using math all the time, everything. And I'm thinking right now about like a small business owner, right? And they have to do pretty basic algebra every day all the time to decide if they can keep their doors open or how they're going to shift and change, right? They may have an equation of we have this online orders and then we have these in-house. Well, now the in-house is closed, so that's obviously impacting the online. Some people, some places, I've heard their business is actually doing better because people are stuck at home. But in a lot, they're not. So algebra is about determining about what we're doing, and I say this to my students every day, is we're practicing, okay? You are on the free throw line of life, of math class, or you're in the batting cage, Okay, I love going to the batting cage. But the batting cage for baseball, softball, whatever, you're going to get essentially the same pitch over and over and over and over. That's the reason why you'd use like a pitching machine, right? Or if you have an actual pitcher, like the pitching coach, they're going to give you a bunch of inside pitches, a bunch of outside pitches, a bunch right down the middle, a bunch low. So you can try to practice those mechanics. We are practicing. We're practicing. I get that sometimes gets a little dull for people learning math, but that's what's happening, okay? You're not doing real new math. You're not. It's not like learning about a poem and then writing a poem, because it's way too heady. So you practice for years before you use it and understand what's going on. Sorry. That's why I geek out about this whole thing, because it's like, oh my gosh, I've been doing this and studying it for years and years and years, and here's a real-time thing happening. It's like unfolding before my eyes. So let's talk about, just simply talk about terms and what are like terms, and then we're going to combine some like terms. All right, but we had to preface this to the beginning of what variables are. So terms, and I put these in quotes because they're not real mathy. But they're things they're phrases people use, and they've become synonymous with math. Which we're going to call, this is the fancy monomial, okay? Mono, one, nomial, named thing, okay? A term would be constants and variables combined under addition. Oh, my goodness, Rebecca Ruth Ann. You just got my full name. Not addition, multiplication. My brain was already somewhere else. That is like the worst kind of mistake, because it's the exact opposite. Multiplication. Sweet Lord. I'm glad I fixed that. Should almost redo the entire video just to fix that one moment. Under multiplication, a singular term. So what are examples? 3 times x. That's a term. Okay? 5 is a term. 12xy is a term. What that means is we have 2 variables. They're different. Right? They're 2 different variables. I know this because I used different letters. These are all terms. Okay? 3 times x, 5 times itself, 12 times x times y. Okay? Here's another term. 7m cubed. Now, we have not talked about exponents yet. We have not. We will, though. We'll talk about everything. So, what are like terms? Well, like terms are any term that has the same variables to the same exponent. I have really bad handwriting, but same variables to the same exponent, like terms. Now, let me erase some of this, and we're going to just do an example in chat. I'm at 9 minutes, but this example will take a hot second. Okay. Because then we do some adding of like terms. But let's just identify like terms. I'm going to give a bunch of terms, okay? I will only use 2 variables, okay? So it doesn't get too confused. X and y, so I'm going to use a and b, all right? So, for a, 12b squared, 7b, 6b, 9ab, 4a squared, 16 a squared b. Okay. Of these 7 terms, which are like terms? Okay, so let's look. This first one here has an a. Okay, so we know in order to find a like term, it has to have an a. B doesn't have an a. Doesn't have an a. This one has an a. Are these two, are 4a and 9ab like terms? Well, let's go over here. It says same variables. I know I have bad handwriting, and I wrote it really fast. Variables, plural. Well, hold on. This one has an a, and this one has an a and a b. So are they like terms? Because let's say for a second we figured out what a is, right? Let's say a is 1. 4 times 1 is 1. 9 times 1 is 1 times b is 9b. Now we'd have 4 and 9b. Those don't have the same variables. Not like terms. So this right here is not like terms with that. It's not like terms with that. Not with that. What about this one? This is a b. Nope. Oh, this one has an a. 4a. And there's no b. Are these like terms? Well, let's check. Same variables, same exponent. Uh-oh. This one, what is this exponent? This is implied. Remember, we talked about this a little bit. We haven't talked a lot about exponents yet, but we will. That's an implicit 1. So this is squared. I'm realizing I'm getting a little glare. Sorry about that. So these are not, nope. And here, it's 2 exponents and a b. So that's not. So this actually does not have a like term with anything for a. None of these. Let's look at 6b. We already know these aren't like terms. Is this a like term? 6b and 12b squared. Well, it's got a b, but it's squared. So no, it's not a like term. Nope. 6b and 9ab. Well, the same conflict we had over here of that, yes, it has an a, but it also has a b. Here, yes, it has a b, but it also has an a. So they're not like terms. We can do the same little test. What if b was 1? You would have 6 and 9a. Those are not the same. So let's look at 6b and 7b. Okay? They both have a b. Do they have any other variable? No. Are they to the same power? 6b to the first, 7b to the first. Oh, thank goodness. We found like terms. Now let's see if is it with this? Nope, that's not a b. And with here we also have the a squared. Are any of these like terms? Well, let's just look at variables now. So now we can do a cut short, right? Because we're starting to learn what we need to do. This has a b squared. So let's just see if it has, it doesn't matter what the number is. This is called a coefficient, by the way. B squared, nope, not squared, no b at all, and not squared, so this has no. AB, nope, a squared and no b. A squared b. This has an a and b, and this has an a and a b, but this one is squared. That's not the same exponent. So this one, these are not like terms. And here's a squared and a squared, but this has no b, and this does. So of all these 7, only 2 are like, okay? This will get faster and easier by sight, like comparing pennies to nickels or nickels to quarters. You'll just be able to tell right away a $5 bill to a $20 bill. Yes, they both have the same physical size and the same touch. If you're blind, you wouldn't know the difference. But when you see it, it's real fast. You'll start to get to that place, but you have to have this form of analysis. Same variables to the same power, same exponent, okay? Those are like terms. Yikes, I got long, but it was a good introduction to variables. All right. See ya. Stay safe.